there are a lot of scenarios in which it's useful to know not just what input gets you an output, that is, what value for x gets you f of x, but also what output would give you a specific input. So let's say, for example, something really basic, you want to figure out what your budget looks like for your classes, where you know that at FGCU, you pay about $150 per credit hour with another $50 that you pay in fees on top of all that. That's not exactly how the budget works, but that's just a quick approximation here to make my numbers nicer. So, if you want to get some value t for your total tuition cost, you can express that as a function f of c in terms of the number of credits c that you're taking as 150c, because it's $150 per credit, plus those $50 in fees. But often you're not going to be in a situation where you want to find out how much you can make for tuition. You're often going to have a budget you have to work within instead. So let's say that if you know that your budget is $1,850, that is, if t is equal to $1,850, and you want to find the number of credits, well, then you have 1850 is equal to 150c plus 50. And solving that is pretty straightforward. I'm not going to show the details there because it's the sort of thing we've been doing fairly regularly since chapter 1, but you can spin those numbers around, subtract a 50, divide out a 150, and you should end up getting that the number of credits you would want in this case is 12, which is a pretty normal semester, right? You're expected to take 12 credit hours, but maybe you're in a program where you need to get more than that. Maybe you're in a program where you need to get less than that. Maybe you have a lot more money and just want to get done quickly. So you want to be able to describe this relationship a bit more generally than just saying, I have my budget, give me the specific number. You want to be able to get any number from that same sort of description in the way that you could plug in a number of credit hours to get a cost. You want to be able to get a number of credit hours given a cost instead. You want to go the other direction? Well, that's not really that hard. For a function to get t, all you do is you take this guy, t equals 150c plus 50, and you solve it for c. Now, this is something that we did at the, I think, end of the first week, where we were talking about adjusting models, solving systems, or equations, for specific variables, but you pull over a 50, you divide out a 150, and you will get that c is equal to t, make that t bigger, t minus 50 over 150, where this function there has a very special name, because what this function does is undo the action of that one, and this one undoes the action of that one in a sense. So if we have that f is, in terms of c, we have f inverse of c, or excuse me, not f inverse of c, f inverse of t is equal to c. And that f inverse is with the notation a -1 in superscript, a power of -1, where in general we have the described relationship f of x equals y happens if and only if, that is, it's equivalent to f inverse of y equals x. The inverse is the reverse of the original. One undoes the action of the other, and we can see that if we look at compositions. Because if we take the composition of f with f inverse of t, we will get our function f evaluated at t minus 50 over 150, which is to say 150 times t minus 50 over 150 plus 50. That ends up simplifying down and just being t. Similarly, if we evaluate f inverse at f of c, we would end up getting 150c plus 50 minus 50 over 150, which just gets us c. So in either case, we end up actually just getting an identity value. We end up getting either c or t, depending on our notation there. And we should be careful with that. For one, this tells us something very important about inverses. That inverses are one of those nice cases, like I said we would get to, where compositions do go both ways. If you compose the function with its inverse or the inverse with the original function, you'll always end up back at the identity. But here, our notation's a little bit different because I represent the inverse in terms of t and the original in terms of c, so you end up with a different variable there. And that's... that probably looks a little bit weird to you all, because I know that with this point, at this point in your algebraic careers, you're used to this very rigid structure of x goes in, y comes out, and that's exactly the way it works. And a lot of times when you see compositions and inverses taught, probably the way you saw these taught in high school was built around that. And I'll mention that way as well. But talking about inverses in that way, for one, it makes them seem kind of arbitrary. And for two, it hides their most interesting property, their central property of being a very specific type of reversal. And you see that best if you flip the relationship between the independent and dependent variable going from one to the other. But we're going to talk a little bit more about this, and I'm going to present the way that you're probably more used to seeing these things. We're going to try and provide some context here to give a better understanding of how it works than that simple rote memorization scheme that you're probably more acquainted with.